Okay, we have a guest appearance here with Keith again. So let's finish off this chapter 2, section 1, where we're going to talk about linear speed versus angular speed. So remember how you find average speed is distance over time. If we want to look at this and say, well, what if we're talking about motion along a circle? Then linear speed would certainly be, if we're talking about a constant speed, this would be our linear. And so let me get another slide here. And so then our linear speed, there we go. Linear speed would be moving at this constant speed, and we would call this distance over time, because once again, when we have our, do my little drawing back here, and remember we said if we wanted to find arc length, we could find it by that distance. And so if we're wanting to find this linear speed, well, how do you find speed? Distance over time. So that's how we would find it. Where then angular is, we're going to be measuring in radians. Angular. Every time I see that, I think of fishing, and I'm not really sure why. Anglers, something, I don't know. And so this formula is omega, and our angle is in radians and then over time. So in other words, this one we're looking at the distance traveled going around a circle. The angular speed just changes to now we're looking at our angle, and again over time. All right, so nice little relationship between these two, and nice for when you work formulas. So if I have this S over T, and we said that S was arc length, which was r theta, remember the last lecture? And so I can say, well, looking here, theta over T is r omega. So that just simply says it's the radius times my angular speed. And once again, where we have to remember that this is going to be in radians. So it makes it kind of nice to have a little shortcut. If you know, if you're looking for linear speed and you know angular speed, then you just simply take the angular speed and multiply it by the radius. So here it says the diameter of each wheel of a bicycle is 26 inches. If you're traveling at a speed of 35 miles per hour, how many revolutions are the wheels turning? So get my pen back here. So once again, we have the drawing up there, but let's kind of draw something here where I'm looking at all the way across is the 26 inches. And so to find the radius, we know we just take half of the diameter. So half of the 26, and we get 13 inches. All right, we already know what the linear speed is because it tells me 35 miles per hour. So 35 miles per 1 hour. All right, so from here now, this is a little tricky because I want to get my linear speed into radians per minute, and it's going to take a couple of steps. So I have this 35 miles per 1 hour, and I can convert this. I know there's 5,280 feet per 1 mile. So as you can see, I've converted it in because the miles cancel. So now I have it in feet per hour, but I want to get this in inches per minute. So there's 12 inches in 1 foot, so the feet cancel. And then finally 1 hour is 60 minutes, so the hours cancel. So now I've gotten this and I've thrown it in a calculator, 36960, but in inches per minute. So I'll multiply all the numerators, all the denominators, and see, dividing, I get this 36,960 inches per minute. All right, so let's use this. Let's get a clean screen here. And so to find this R omega, okay, so my linear speed, we said that this was a shortcut. Well, if I take this and I solve it in terms of omega, I know I just found this to be 36,960 inches per minute. And I know the radius is 13 inches. So now certainly you can see why we needed to get it in inches. And so if I multiply this out, the inches cancel and I get 2843.08. And in this case, since the inches canceled out, and of course the minute's going to go to the bottom, remember that we said that omega is measured in radians, so this becomes radians per minute. I'm asked to find how many revolutions, so turn this into revolutions, 2843.08 radians per minute. I remember that one revolution is 2 pi radians. So I canceled out my radians and again divide the 2 pi into the 2843 and you should get 452.5 revolutions per minute. All right, so it took a couple of steps to see all the conversions that I had to do, which is probably was the hardest part on that one. All right, so this next one is actually my math lab question. It says you have 2 pulleys. So I have, let's say, this pulley here, and I have another pulley here, and there's a belt that's connecting them. So it's running like that. Says one has a radius of 2 inches and one has a radius of 8 inches. So that's what my picture looks like. Okay, so 2 pulleys, radius with 2 inches, one with 8 inches, and they're connected by this belt. Okay, we can double it up. And this belt, and it's just running around and around and around. It says the 2-inch pulley is caused to rotate at 3 revolutions per minute. So what I can do here is if I want to find the revolutions per minute of the 8-inch one, okay, they give me the 2-inch one, then I know the linear speeds because of this belt moving. The linear speeds are the same, okay, because the belt's moving both of these, the same linear speed are the same as the speed of the belt. All right, so let's call R1 the smaller one. We'll call this one R1 and this one R2. And so radius 1 is 2 inches. And I know the angular speed is 3 revolutions per minute. That was given to me right there. Well, we said these are equal, so let's set this side up over here. My R2 is 8 inches, and then my omega 2 is what they're asking me to find. So that's the part I'm actually trying to find. Well, in this case, my revolutions per minute, I need to get in radians per minute. Okay, so to do that, I know 1 revolution, once again, is 2 pi radian. So if I multiply this by 2 pi, and this gives me 6 pi radians per minute. All right, setting these equal, because that's what we said, is that the linear speeds are equal. So I'm going to kind of do that over here. So my two linear speeds are equal. How do we find linear? The radius times our angular. The radius times our angular. I just plug in everything that's given. The 2, in this case, I changed to radians because we said that angular needs to be in radians. I have 8. And now I have something that I can solve for omega 2. Looks like 12 pi over 8. And then finally, the very last thing I need to do, it wants it in revolutions per minute. So to convert this in revolutions per minute, all I have to do is divide by 2 pi to get the radians out of there, which gives me 12 over 16 or 3/4 revolutions per minute. Okay, so that one's kind of a little weird, but the big key was to recognize that the linear speeds are the same, okay, because of this belt. It's just one belt, it's not two different belts. After I figure that out, I figure out, well, what are the linear speeds? Well, we said linear speed is r times omega. I know what my r is for both of them. I only know what my omega is for the smaller belt, which is fine, or the smaller pulley. And I'm looking for the larger one, and it says find the revolutions per minute. So that was this very last step that I actually had to convert. All right, so have fun with these, linear speed, angular speed, work lots of examples, until you get them down. The formulas aren't too difficult. I think the hardest part is figuring out how to convert things into the answers that your lab wants it in. Any questions? Be sure and ask me.